Hi students, in this video we are going to talk about total probability theorem, Bayes theorem and their applications. Okay, let me get started with a problem. Suppose a calculator manufacturer purchases his ICs integrated circuit boards from supplies B1, B2 and B3 with 40% from B1, 30% from B2 and 30% from B3. Suppose 1% of supply from B1, 5% from B2 and 10% from B3 is defective. There are two questions here. Question 1. What is the probability that a randomly selected IC from manufacturer stock is defective? Question 2. Suppose a randomly selected IC is found to be defective, then what is the probability that it was supplied by supplier B1? Okay, let's try to answer these two questions. Okay, solution. Here, a random IC selected from manufacturer stock. So the sample space omega is going to be all manufacturer stock. Okay, now let Bi denote the event that selected IC come from supplier Bi for I equal to 1, 2, 3. Okay, so we just defined three events B1, B2, B3. Now we can see that no IC come from more than one supply and any IC in the manufacturer stock come from one of the supplier B1, B2, B3. So we can see Bi intersection Bj equal to Mt for I naught equal j and B1 union B2 union B3 going to be all omega. That means B1, B2, B3 form a partition for omega. Fine. Now let's try to answer question 1 here. Let D denote the event that randomly selected IC from stock is defective. So we are interested in probability of D here, right? And we know that 40% of supply from B1, 30% from B2 and 30% from B3, right? So the probability of B1 equal to 0.4, that is probability of randomly selected IC come from supplier B1 is 0.4. Similarly, probability of B2 and probability of B3 both are equal to 0.3. And we also know that 1% of supply from B1 is defective and 5% of supply from B2 is defective and 10% of supply from B3 is defective. That is, the probability of D given B1 equal to 0.01. That is, probability of randomly selected IC is defective given that it is coming from supplier B1 is 0.01. Similarly, probability of D given B2 is 0.05. Probability of D given B3 is 0.1. Okay, now look at this picture. Here, the whole manufacturer stock is this rectangle which is divided into three portions. The yellow portion consisting of ICs from supplier B1, the green portion consisting of ICs from supplier B2, the blue portion consisting of ICs from supplier B3. Now the ellipse portion you see that consisting of defective ICs in manufacturer stock. As you see, some defective ICs come from B1, some defective ICs come from B2, and some defective ICs come from B3. So as you can see that D is union of three portions, that is orange portion and brown portion and purple portion. So D we can write D intersection B1 union D intersection B2 union D intersection B3. Okay, as you can see from the picture, the D is union of these three portions. Now the probability of D going to be probability of the right hand side. Now B1, B2, B3 are mutually exclusive. That implies D intersection B1, D intersection B2, D intersection B3 also going to be mutually exclusive. So this probability of the right hand side we can write by finite additivity sum of the probabilities like this. Now we can apply multiplication theorem on each term here. So we can write like this. Here this probability of D intersection B1 we can write probability of D given B1 times probability of B1 by conditioning on B1. Similarly, probability of D intersection B2 we can write like this. Probability of D intersection B3 we can write like this using multiplication theorem on each term. Okay. Now we have everything. We have these probabilities and we have these conditional probabilities. Okay. So let's plug it here. So the whole sum gets simplified to 0.049. Therefore, the probability of a randomly selected IC from manufacturer stock is defective is 0.049. Okay, fine. Now let us try to answer question 2. In question 2, the randomly selected IC is found to be defective. Then what is the probability it was supplied by supplier B1? That is, we are precisely interested in probability of B1 given D. That is, probability of randomly selected IC come from supplier B1 given that it is defective. Okay, fine. Now, by using definition of conditional probability, we can write probability of B1 intersection D by probability of D. Okay. Now again, by applying multiplication theorem in the numerator, we can write the numerator like this. Probability of D given B1 times probability of B1 using multiplication theorem. Fine. Now we know everything here. Probability of D given B1 is 0.01 as 1% of supply from B1 defective, and probability of B1 is 0.4 as 40% come from supplier B1, and probability of D we got from part 1 0.049. Now let's plug it here. So this whole thing gets simplified to 0.08163. Therefore, the probability of B1 given D is 0.08163. So we answered the second question. Similarly, one can be interested in probability of B2 given D and probability of B3 given D. They can also be worked out in similar fashion. Okay. Fine. Now, let me introduce some terminology with respect to above problem. Here, the probability of BIs for I equal to 1, 2, 3 are called priori probabilities because these probabilities are assigned prior to pick an IC and see any evidence about D. Okay. And probability of BI given D's for I equal to 1, 2, 3 are called posterior probabilities because these probabilities are calculated after picking an IC and looked at the evidence that D happened. Okay, that's why these are called posterior probabilities. And the probability of D given BIs for I equal to 1, 2, 3 are called likelihood probabilities because these probabilities indicate likelihood of defectives in each supplier. Okay, fine. Now, what we did in the question 1 of the problem is going to be generalized as total probability theorem, and what we did in the question 2 of the problem is going to be generalized as Bayes theorem. Okay. Now we are going to see total probability theorem. Okay, total probability theorem. Here is the statement that E1, E2, so on, En are n events in event space, each with a positive probability, which form a partition for omega. Then, for any event E in event space, the probability of E equal to summation I equal to 1 to n, probability of E given Ei times probability of Ei. Okay. Now let's prove this statement. Proof. Here, E1, E2, so on, En form a partition for omega. That means they are mutually exclusive and exhaustive. So, we have Ei intersection Ej equal to Mt for I naught equal to J, and their union I equal to 1 to n Ei going to be equal to all sample space omega. Fine. Okay. Now, For any event E in event space, we can write E equal to E intersection omega because E is subset of omega, right? So E equal to E intersection omega. Now let's replace this omega using this union. Now let's replace this omega with this union I equal to 1 to n ei. Now E equal to E intersection union I equal to 1 to n ei. Now apply the distributive laws, then E can be written as union I equal to 1 to n E intersection ei. Just like in the above problem, we wrote D equal to D intersection B1 union D intersection B2 union D intersection B3, where B1, B2, B3 form a partition for omega. In this case, here E1, E2, E3, so on, En form a partition for omega, and E we are writing as E intersection E1 union E intersection E2 union, so on, E intersection En. Fine. Now the probability of E going to be same as probability of the right hand side. Again, mutually exclusiveness of E1, E2, En implies mutually exclusiveness of E intersection E1, E intersection E2, so on, E intersection En. So the right hand side probability going to be sum of the probabilities by finite additivity. Now, so the probability of E equal to summation I equal to 1 to n probability of E intersection Ei. Now we can apply multiplication theorem on each term of the summation. We can write the probability of E given Ei times probability of Ei by conditioning on Ei. Let's do that in next step. So therefore the probability of E equal to summation I equal to 1 to n probability of E given Ei times probability of Ei. So this is the total probability theorem, due to multiplication theorem on each term. Fine. In this expression, the probability of Eis are called priori probabilities and probability of E given Eis are called likelihood probabilities with respect to event E. Here, the probability of E can be seen as weighted average of likelihood probabilities with the weights being corresponding priori probabilities. Fine. Now question is when to apply this total probability theorem. See, you may be interested in probability of some event E which can caused by exactly one of the event E1, E2, so on, En, which form a partition for omega. And you know this probability of Eis, which are priori probabilities, and this likelihood probabilities. Then we can talk about probability of an event E using total probability theorem. Fine. Next, corollary Bayes theorem. Again, statement is in similar setup. Let E1, E2, so on, En are n events in event space, each with a positive probability and which form a partition for omega, and is any event in event space with a positive probability, then the probability of Ei given E equal to probability of E given Ei times probability of Ei by summation j equal to 1 to n probability of E given Ej times probability of Ej. For any I equal to 1 to n. This is the Bayes theorem statement. Let's prove it. The proof, the probability of Ei given E equal to by conditional probability definition, the probability of Ei intersection E by probability of E. So in the numerator we can apply multiplication theorem, then we can write probability of E given Ei times probability of Ei. In the denominator we can use total probability theorem. So the next step we can write like this. In the numerator we applied multiplication theorem, in the denominator we applied total probability theorem. So therefore we have this, probability of Ei given E going to be probability of E given EI times probability of EI by total probability summation j equal to 1 to n probability of E given EJ times probability of EJ. Okay. So here the probability of EI given EIs for I equal to 1 to n are called posterior probabilities. Okay. So now when to apply Bayes theorem? Bayes theorems are used to calculate posterior probabilities. What are the posterior probabilities? Here say we have an event E which can happen due to exactly one of E1, E2 so on En which form a partition for omega. Okay. Now you performed an experiment and you see the evidence that E happened. Now your interest is what is the probability E happened due to E1? What is the probability E happened due to E2? And so on. Okay. These probabilities are called posterior probabilities. For example, in our IC's problem, the defective IC may caused by B1 or B2 or B3, right? There we selected IC and we found it to be defective. Now then our interest was what is the probability this defective IC coming from B1 supply. Okay, that is a posterior probability. So Bayes theorem is used to calculate posterior probabilities. Okay, problem. Say government is decided to test everybody in your city for COVID-19. So you got tested for the same. And the test is 98% effective in detecting coronavirus when it is in fact present in your system. However, the test also yields a false positive result for 1% of healthy persons tested. And government estimates that 0.5% of the population in your city probably got infected with COVID-19 as of now. What is the probability that you really got infected by virus if your test result is positive? Interesting. Okay. Here we are interested in posterior probability because see here the test is not perfect. Here healthy person can get a positive result, infected person also get a positive result. Okay, here you got tested and we see the evidence that your result is positive. Okay, now here we are interested in what is the probability this positive result due to virus. Okay, this is a posterior probability, so we are going to use Bayes theorem to calculate this probability. Fine. Now here say you are a random person in your city. Okay, so the sample space is going to be your city population. Let D denote the event that randomly selected person has a virus in his or her system. Okay, then D will consisting of virus infected people in your city, then D complement will consisting of healthy people in your city. Okay, so the whole city population fall into two types, virus infected people and healthy people. So here D complement form a partition for omega. Okay, let E denote the event that random person test result is positive. Okay, here we are interested in probability of D given E, that is probability of person is infected by virus given that its test result is positive. Okay, fine. Here it is estimated that 0.5% of the population probably got infected by virus. So the probability of D going to be 0.005. Okay, that implies probability of D complement is 1 minus probability of D, that will give you 0.995. Okay, these are priori probabilities. Okay, now the likelihood probabilities, the probability of E given D is 0.98 because test is 98% accurate. That is, the probability of person result is positive given that person has a virus is 0.98. And the test also has false positive rating 1%. That is, probability of E given D complement is 0.01. Probability of person result in positive given that his health is 0.01. Fine. Now, from Bayes theorem, probability of D given E we can write probability of E given D times probability of D by probability of E given D times probability of D plus probability of E given D complement times probability of D complement. Okay, this is from Bayes theorem. Now we know all these probabilities, okay, priori probabilities and likelihood probabilities. Now let's plug it here. Okay, so this whole thing gets simplified to 0.32996 something. Okay, that is probability of D given E approximately 0.33. Thus, only 33% of those persons whose test result is positive by this test actually have virus in their system. Okay, result must be surprising for you. You didn't think the test is this bad, right? What is the matter? Is Bayes theorem nonsense? Don't say that yet. Okay, let's try to verify the answer intuitively. Okay, fine. Now, let's try to answer the same question intuitively. Fine. Say the population size is 200, in which 0.5% of the population infected. So, 1 is infected, 199 are healthy. Okay, so total number of positive cases we will get is this. See, 1% of healthy people get a positive result, 98% of infected people will get positive result. So 1% of 199, which is 1.99, 98% of 1, which is 0.98, the total is 2.97. So the total positive cases we will get is 2.97, in which correct positive cases are only 0.98. So the proportion of the time the test result is correct when test say positive is correct positive cases by total positive cases, which is 0.98 by 2.97, which result in 0.329966 so on, which is exactly what we got from Bayes theorem. So Bayes theorem is not nonsense, which perfectly makes sense. Okay, the reason test seemed good because we have a bad intuition. Our intuition is supposed to be like this. Okay. Anyway, Bayes theorem is perfectly makes sense. Okay, fine. Okay, problem. Let S be a set with n elements. Suppose we pick two elements a comma b at random from power set of S, one after another with replacement. So that first one, probability of b subset are equal to a is 3 by 4 to the power of n. Second one, probability of a intersection b equal to mt is also 3 by 4 to the power of n. Okay. Here, the random experiment is picking two elements a comma b at random from power set of S, one after another with replacement. Okay. Here, outcomes can be observed like this. Order pairs a comma b, where a, b are elements of power set of S. Okay. This set can be described as Cartesian product of power set of S with power set of S. Okay, that's why the sample space omega can be seen as Cartesian product of power set of S with the power set of S. So the number of elements in omega are going to be number of elements in this Cartesian product. Okay, and we know that if S having n elements, power set of S will have 2 to the power of n elements. Power set of S is set which consisting of subsets of S. Okay, so the number of elements in part set of S cross part set of S is going to be 2 to the power of n times 2 to the power of n, which is 4 to the power of n. So here the size of the sample space is 4 to the power of n. Okay. Now let ei be the event that A having size I. No condition on B, but A should have a size I. Okay. So the number of elements in ei is going to be n choose I times 2 to the power of n, because here I want to pick any subset of size I. There are n choose I subsets of size I for S. If S having n elements, then there are n choose I subsets of size I. So A can be anything from those n choose I subsets. So n choose I ways we can pick A. Then B can be any subset of S. There are 2 to the power of n subsets for S. So B can be any one of those 2 to the power of n subsets. So B can be picked in 2 to the power of n ways. That's why the number of elements in ei is going to be n choose I times 2 to the power of n for any I equal to 0, 1, 2, so on n. Now here E0, E1, so on, En form a partition for omega, because whenever we perform an experiment, exactly one of these E0, E1, so on, En happen. Okay. Now, first one, let E denote the event that B subset are equal to A. We are interested in probability of E, right? Okay. Now first let us look at probability of EI. Here we are picking elements of part set of S at random, so we can assume outcomes are equally likely. So we can use classical definition to compute probabilities of events, right? So the probability of EI is going to be number of elements in EI by number of elements in omega, and we already got number of elements in EI equal to n choose I times 2 to the power of n, and the size of the sample space is 4 to the power of n. So this gets simplified to n choose I by 2 to the power of n. So therefore, the probability of ei equal to n choose I by 2 to the power of n for all I equal to 0, 1, 2, so on, up to n. Okay, now let's also look at probability of E intersection ei. Okay, the probability of E intersection ei going to be number of elements in E intersection ei by number of elements in omega. Number of elements in E intersection ei going to be n choose I times 2 to the power of 5. Here you want ei and E both to happen, right? If you want ei to happen, you must pick A of size I. There are n choose I ways you can pick A of size I, because there are n choose I subsets of S of size I, right? Fine. Now, if you want E to happen, B should be subset of A. If A having I elements, there will be 2 power I subsets for A. So B can be any one of those subsets. That's why B can be picked in 2 power I ways. Okay, so that's why number of elements in E intersection ei equal to n choose I times 2 to the power of 5. Okay, so therefore the probability of E intersection ei equal to n choose I times 2 to the power of 5 by 4 to the power of n for all I equal to 0, 1, 2, so on n. Okay, now let us look at the conditional probability of E given ei. The probability of E given ei according to conditional probability definition, probability of E intersection ei by probability of ei. Now here the probability of E intersection ei we got here n choose I 2 to the power of I by 4 to the power of n. The probability of ei we got n choose I by 2 to the power of n. Let's plug it here. So this gets simplified to 2 power I by 2 to the power of n for all I equal to 0, 1, 2, so on n. Okay, fine. Okay, now here this probability of EIs are priori probabilities because E0, E1, so on, En form a partition for omega, and the probability of E given Es are likelihood probabilities of E. Okay, fine. Now, from total probability theorem, the probability of E equal to summation I equal to 0 to n probability of E given Ei times probability of Ei. Now we have everything in this expression. Let's plug it here. So summation I equal to 0 to n, the probability of E given Ei we got 2 power I by 2 to the power of n, and the probability of Ei we got n choose I by 2 to the power of n. Okay, so now in the denominator, this 2 to the power of n, 2 to the power of n, if you take out, you'll get 1 by 4 to the power of n common. So 1 by 4 to the power of n, summation I equal to 0 to n, n choose I times 2 to the power of I. Now, using binomial theorem, this is exactly expansion for 1 plus 2 to the power of n. So therefore, the probability of E equal to 3 by 4 to the power of n. Okay, fine. Next. Okay, now let us try to answer the second one. Here we should know that A intersection B equal to empty if and only if B is contained in A complement. So computing probability of A intersection B equal to empty would be same as computing probability of B is contained in A complement. Okay, we'll try to compute probability of B subset of A complement. Okay, let Fi denote the event that A complement having size I for I equal to 0, 1 to so on n. Here we pick two elements from power set of S, A and B, and we want here Fi denote the event that A complement having size I means that happen if and only if A having size n minus I. Okay, so the number of elements in Fi going to be, first we are picking A. The A should be of size n minus I, so that A complement will have size I. So A can be picked in n choose n minus I ways. Now there is no condition on B. B can be any subset of S. So there are 2 power n subsets. So B can be picked in 2 power n ways. But we know that n choose I same as n choose n minus I. So this n choose n minus I can be replaced with n choose I. So that's why the number of elements in Fi equal to n choose I times 2 to the power of n for I equal to 0, 1 to so on n. Fine. Now, here again F0, F1, so on, Fn form a partition for omega, because whenever we perform an experiment, exactly one of F0, F1, so on, Fn happen. Okay, because A complement got some size from 0 to n. Okay, so fine. Now let F denote the event that B is contained in A complement. This happens if and only if A intersection B equal to empty. Okay, so we are interested in probability of F. First let us compute probability of Fi. The probability of Fi is going to be number of elements in Fi by number of elements in omega. We already got a count for number of elements in Fi, which is n choose I times 2 to the power of n, and size of the sample space is 4 to the power of n. So this gets simplified to n choose I by 2 to the power of n for I equal to 0, 1, 2, so on n. Okay. Now let us compute probability of F intersection Fi. The probability of F intersection Fi going to be number of elements in F intersection Fi by number of elements in omega, and the number of elements in F intersection Fi. See, F intersection Fi means we want both F and Fi to happen. First of all, if you want Fi to happen, A should have a size n minus I, because A complement should have a size I, so A should have a size n minus I. So A can be picked in n choose n minus I ways. Now B should be subset of A complement. If you want Fi to happen, B should be subset of A complement. A complement will have size I because A having size n minus I. So A complement having size I. So B can be any subset of A complement. So there are 2 power I subsets. So B can be picked in 2 power I ways. So that's why the number of elements in F intersection Fi going to be n choose n minus I times 2 to the power of I. So the number of elements in F intersection Fi, we are writing n choose n minus I times 2 to the power of I by size of the sample space is 4 to the power of n. But we know that n choose n minus I is same as n choose I. So the probability of F intersection Fi going to be n choose I times 2 to the power of I by 4 to the power of n for all I equal to 0, 1, 2, so on n. Okay. Now we compute these conditional probabilities. Probability of F given Fi according to definition of conditional probability, which is probability of F intersection Fi by probability of Fi. We have this both. Okay. Now first probability of F intersection Fi is this part. You plug it here. Probability of Fi is this part. We plug it here. This gets simplified to again 2 power I by 2 to the power of n for all I equal to 0, 1, 2, so on n. Fine. Now we got this priori probabilities, probability of Fi's, this likelihood probabilities. Okay. Now by total probability theorem, the probability of F going to be summation I equal to 0 to n probability of F given Fi times probability of Fi. Now we have everything in this expression. Let's plug it here. So the probability of F given Fi, we got 2 to the power of I by 2 to the power of n. So we plug it here. The probability of Fi, we got n choose I by 2 to the power of n. We plug it here. Again, just exactly same expression as we did in the part 1. So this gets simplified to 3 by 4 to the power of n. Okay. So fine. That's it. Okay, now let me stop.